Hi, welcome back. So I think I've been talking not a bit, about coordinate systems, and I want to talk a bit more about that. Coordinate systems, it seems to be an idea that confuses people new to graphics. So I'll talk a little bit more about that. The reality is, and I've said this before, is that coordinate systems they're completely virtual. We make them up. Just like on paper, you can make up your own coordinate system. On computers, we do too. And it's important to realize that not only can we make them up, we do. And we change coordinate systems based on what our needs are. So we've seen a few, right? We did the two triangles example. And this one was kind of neat because the coordinate system we used here was x went from -1 to +1, y went from -1 down this side to +1 up here, and the center then was right in the middle with y going up and x going to the right? And then we had our blue triangle here, and then um, our red triangle down here, whatever it looked like. Okay, and then our point here was just 0.35, 0.1 or whatever in this coordinate system, but it still looked the same on the screen. This is called the unit coordinate system, and the reason it's unit is because of those ones, plus or minus one. So we'll come back to that a little bit later. If you peek at our code, you'll see that we used a command called ortho. Again, we'll learn about projections later, but this sets up a straight projection with no perspective, so it's just straight. And then we use -1, 1, 1 minus 1, and this is left. So this is the left side of the boundary, right, bottom, and then top, like that. And so you set that up, and you'll get that coordinate system on your display. Of course, I also have my code reset matrix. You shouldn't have to do this in OpenGL, but this is a processing thing. In your setup, you should do these things. You reset the matrix because it'll have other things that conflict. It took me hours to figure out why my graphics wasn't working properly. Um, I had to use this reset matrix business. So that was one coordinate system we saw. And then the processing coordinate system is different from this. Again, exact same screen, exact same viewport, but you should be more familiar with this from your 1010 days. 0 is up here, the origin is up here. This is 0, 0 is up there. X goes this way and then Y goes down. And we can just draw the same thing, right? You can draw the same thing, but now, even though on the screen it can look identical, there are different coordinates. And I took this from my notes. 432, 288 is this point. Same on the screen, exact same pixel, but we use different coordinates to get there because our viewport is set up with a different coordinate system. And then in OpenGL standard, the origin is down here, and then the x goes this way and the y goes up this way. So it's flipped y for processing. Again, same triangles. We can get the same results, but in order to do it, we do have to use different coordinates. So again, 432 again, the same x coordinate, but instead of y at 288, we need to set it to 352. Now we can do the conversions on math, but don't worry about it. The key point here again, though, are that these coordinate systems, they're just virtual. We make them up and we choose them based on what's useful. This one on the left here is called a unit coordinate system because it goes from -1 to 1, -1 to 1. These processing in the OpenGL ones, these are more pixel coordinate systems, right? And the reason these are called pixel coordinate systems is because the idea of one unit in our space refers to one pixel on the screen, right? So in both these examples here, I have 640 by 640 as my corner, and this one up here is the opposite corner. Key message: you just need to know your virtual system, and as we said before, coordinate systems are virtual. They're just made up. They're just for representing your data. They're all made up in computers. It's all in memory until it hits the physical raster. And this is nice, right? Because you can change the DPI settings in Windows, you can change your monitor with different number of pixels, and still get roughly the same thing coming out. Maybe less and more detail depending how many pixels you have, but it can do that conversion at the last minute. And coordinate systems, we select them for convenience, and we select them for convention. Right? If you're doing something from math and you're familiar with a certain coordinate system, it just might feel comfortable, or it might make sense for you to use the same coordinate system. So I'm going to introduce some vocab here. What we want to do is we specify our shapes in some coordinate system, okay? Or specify our drawings. Okay, we specify our shapes in some coordinate system. But then, to go from these virtual ones that I talked about to the screen, we need to transform them. And in fact, it's not usually one transformation like you might think. Oh, well, it's -1 to 1. I know my screen. Let's do one transformation. It turns out that your coordinates are going to go through many transformations along the way, especially when we get to 3D. It'll transform again and again for different purposes, and we'll learn a lot about that. So then the graphic system will transform them. They are transformed through other coordinate systems until it reaches the screen. So another way of saying this is rasterization, which is this whole unit. So rasterization takes us through a series of transformations. I'm going to highlight those. Transformed. Through a series of transformations to display pixels. For example, we might have our, I'm going to change colors here. We might have our, a triangle in some virtual space, right? -1 to 1, -1 to 1, whatever. And then we need to convert that into our viewport coordinates. But our viewport is actually on a monitor full of windows and taskbars. This is your start button and your taskbars, and there's other windows, and our viewport is over here. So you need to convert it into your viewport coordinates. And then, of course, this is actually on a physical monitor, right? This is my physical monitor on a stand. And then on here, we have all of these things, and our triangles in here somewhere again. So all of these stages, you can imagine, we have transformations. And then finally, this physical monitor has a grid, and we need to fill in our pixels with numbers, values to get our triangle. Okay, so each one of these stages is important, and each one has its own transformation. So it'll actually change coordinate systems quite a few number of times. So this last stage of rasterization here, where you actually get to the pixels, is actually quite complicated. This last stage of converting this final, we're in vector as long as we can, and then finally we convert from vector to pixels. This uses, it should be an E, let's fix that. It looks ugly. A series of algorithms. It turns out you need to use some linear algebra. It gets complicated fast, and we'll get into that. But this is, so far we've learned about rasterization, how we go through all these coordinate spaces to go towards the vector, but we won't get to this last stage quite yet of turning our vector into pixels. That'll have to come next, okay? I want to go through a couple of slides. Slides 19 to 23 in our set that we have. Where is it? Okay. Good, we can see that. So here's an example of the viewing pipeline. So I kind of drew this in my slides. So we start with some object coordinates. We do some transformation. We'll learn about modeled and view transformations later, but you'll do that to get into the world coordinates. It's still virtual, of course. We do clipping, which is deleting things that you can't see. If you transform things and it's off the screen, then let's not bother drawing it. That's called clipping. And there's also projection, which emulates the real world or camera, where, you know, for example, things further away or smaller. We'll get to that too. And then we finally arrive at what we call normalized device coordinates. And this is often this -1 that I've been talking about, this unit coordinate system, but they're normalized, independent of your device. And then we get this final rasterization step where we convert the vector into pixels and we move to window coordinates. So here's an example. I have pixels, I have my triangle. At this very last stage, I need to actually light up pixels and choose what colors they are based on that vector graphic, based on those lines of that pencil. There we go. Here we are. So this is what the final phase of rasterization looks like. It's actually really tricky, right? We can imagine we zoom into the pixels here and we draw these lines, but then we have to choose which pixels as a red triangle to light up. So this one, it goes through the blue square, but only a bit, so we'll keep it blue. This one's mostly red. These ones it just touch. So you have to make that decision. Do you color every single square that it touches, like this one, this one, this one, or not? And how do you figure out which squares it touches? It actually gets complicated very quickly, but we need to make those decisions for every single pixel. In fact, these pixels here are called fragments. If I'm shading my pixels, I'm doing this triangle. These are my fragments of my triangle. Each one of these is one fragment, and we have to determine which fragments we need to shade red. It gets challenging really quickly. This fits into the OpenGL pipeline. The OpenGL pipeline is the standardized way that OpenGL renders things. So you can see triangle, it gets rotated and transformed a bit. Then we have rasterization. Vertex data, we call that. That vertex data in OpenGL or in graphics card, that's just points, your vertices for your triangles or your other shapes. That's all it is. Then you do vertex operations. You do transformations. You change coordinate systems. Then you do rasterization. You turn it into fragments. You say, okay, these are my fragments of my triangle. The other ones don't touch them. You can do other things with fragments, like for example, what's called texture mapping. I can take pieces from an image data and I can apply that and paste that on my triangle. That's called texture mapping. We can do other things like lighting, which simulates reflections and things like that. And finally, once we have our fragments all set up, then they go into our frame buffer, and all of our frame buffer stuff from another lecture pops up. So this is a simplified version of what OpenGL does, and pretty much any graphics system will do. Vertex data, you do operations on them, you rasterize it to get fragments, you do operations on those fragments, and you finally work in the frame buffer. So there's a lot of stages, a lot of steps that have to happen to get graphics to work. Here's a complete OpenGL pipeline. Don't worry about it. You go from, we will learn most of this by the time you're done, but not necessarily all of it. So we start with vertices, they go all transformed. Then we have primitives assemblies. These are like our triangles and quads, those kinds of things. We make fragments, and then we turn fragments into pixels. And then the frame buffer here is the last component of that. So don't worry too much about the details, but it might be worth your time or be interesting to sit here and peek over things and see what you know and see what you don't know. So some key terms for you from this section. We should know these. Let's go through them. Fragment. I just talked about that. That's not a pixel. It's a piece of your triangle or your thing you're trying to rasterize that needs to be shaded or turned into a texture or something. The frame buffer we know. Immediate mode we learned about. GPU, pixel, rasterization, rendering. Rasterization is the problem of getting it into pixels. Rendering is a problem of taking abstract data and getting it to graphics. They're similar, there's overlap, but they're not the same. There's transformations, things that we do to our coordinates. There are vertices and vertexes. We have viewports. We learned about window coordinates. And I mentioned world coordinates, but that'll make a bit more sense later. But what's cool about this is through this unit, probably most of you never heard of most of these before. Maybe pixel, you could have guessed at vertex, but now you've learned all of these other ones. All right, so that's it. We'll use that. We'll finish the unit there. And yeah, we'll continue on to the next unit. Thanks.